So we are going to summarize some of the discoveries that we've made in class that we've done with the calculator, and we noticed things about their end behaviors. So here's a couple of the ones that hopefully we have already written down, but if not, you can write them down now. If the polynomial is of odd degree and we have a positive leading coefficient, then the end behavior is down and up. If the polynomial is an even degree and it's positive, it goes up and up. And then now, if the leading coefficient is negative, then the end behaviors just switch. A polynomial has turning points, one less than its least degree. The important critical points on the graph are x-intercepts, y-intercepts, and any turning points. And remember, turning points are maximums and minimums of the graph. And because of the fundamental theorem of algebra, the degree is equal to the number of solutions. All right, so we're going to do a couple of examples describing the end behavior. We're going to identify the degree and then also what the leading coefficient would be. So here we go. So if we look at this polynomial, we're looking for the degree. The degree is the highest exponent. So 4. So our degree is 4. Our leading coefficient is the number in front of the term with the highest exponent. So if this was our degree is 4, our leading coefficient is 3. So that being said, our end behavior, the degree is even. Our leading coefficient is positive. And so if you go back to that chart, even and positive means that our graph is going to have end behavior that is up on the left and up on the right. Okay, so up and up. Let's look at the second one. Our degree is our highest exponent, so we have 3. Our leading coefficient is -2. So now to describe the end behavior, our degree is odd. It's an odd degree. And we have a negative coefficient. So generally, odd graphs go down on the left and up on the right. But because we have a negative leading coefficient, that's going to get swapped. So it's going to be up on the left and down on the right. All right, we're going to look at determining the number of real solutions and the number of imaginary solutions given a graph. Now, the fundamental theorem of algebra says this. It says that the degree equals the number of solutions. Now, those solutions could be real or they could be imaginary. We have talked about that with parabolas. We can see real solutions. Real solutions are where the graph hits the x-axis. So, let's look at example 1. This one is telling us that this is a degree of 4. Let's count up how many times it hits the x-axis. There's 1, there's 2, there's 3, there's 4. If our degree is 4, we have to have 4 solutions. Now, because I can see all 4 of them, they're all real. So this would be 4 real solutions. All 4 of them are real. And we could also describe our end behavior. Let's go ahead and do that. This end behavior would be down and down. The degree's even, so they're going in the same direction. The leading coefficient, is it positive or negative? I wonder. Just wonder if you can answer that question. Perhaps I'm going to ask you that on the Google form. Okay. What is the leading coefficient in example number 1 of the graphs? All right, let's look at example number 2. Example number 2 has a degree of 3, so that means it has to have 3 solutions. Let's count them up. Let's see how many of them are real. Here's 1, there's 2, there's 3. So we have 3 real solutions. All right, let's look at example number 3. This one has a degree of 3. So we have to have 3 solutions. Let's see how many of them are real. 1. So we have 1 real solution. Oh, I thought we were supposed to get 3. What do you think the other 2 would have to be? The other 2 are imaginary. We can't see them. So this has 2 imaginary solutions. We can't see them graphically, but they do exist, and we will work on the following week on how we would actually figure out exactly what those solutions are. Right now we're just counting them and classifying. So 1 real solution I can see and 2 imaginary solutions. The other important thing that I think we need to note here is that imaginary solutions always come in conjugate pairs. We're going to talk more about that a little bit later. Right now, all I want you to know is that I could never get 1 imaginary solution. That is impossible. That cannot happen. You always have to have an even number of imaginary solutions because they have to come in pairs, like a pair of shoes. You never wear one shoe, right, on your foot. They have to come in pairs. So imaginary solutions always come in conjugate pairs. Okay, so I will see you in class next time, and we will I'll have you practice a little bit about finding end behavior from a graph, end behavior from an equation, the leading coefficient, and whether or not that makes the end behavior, okay? And then also how many real solutions and how many imaginary solutions given a polynomial graph. All right, see you then. Bye.